10, section 3 is dealing with alkenes. So we've been spending our time so far talking about alkanes, singly bonded carbon chains. Now we're talking about alkenes. Slight letter change makes all the difference. So the very basics of this. First of all, and we learned with alkanes that there's a general formula of CnH2n plus 2. Now with alkenes, we're down to CnH2n. And my question for you is where we've seen this formula before. And if you think back to our very beginning of alkanes, where we had CnH2n plus 2, that was with a straight chain alkane. But if we had an alkane that was cyclical, let's say we have a carbon ring with 6 carbons around it, and we had hydrogens filling up the rest of the necessary 4 bonds for carbon. We find that even though it's an alkane, because it's all singly bonded, I don't have C6H14 like we would expect for an alkane. That's a no. What we do have is C6H12. So that's like the formula that we have up here, CnH2n. So when I had a cyclical alkane, I had that formula as opposed to the general alkane formula. So that's where we've seen that before. The reason we have this is because we contain a single a single carbon-carbon double bond, which means we've lost 2 electrons, or 2 hydrogen, because we don't need those 2 hydrogen to fill out the carbon bonds, because we have that extra double bond. And we call this unsaturated. We can have either whenever we contain a double bond, which is alkene, or when we have a triple bond present, an alkyne. These are unsaturated because there's extra places where theoretically we could have had hydrogen before. If we have an alkane, so all single bonds, we are saturated because we have the maximum amount of hydrogens. So it's all dealing with hydrogens. We have the maximum amount of hydrogens around the carbons. The 5 most common isomers for the first, most common isomers for the first 5 alkenes are below. You have this chart in your notes. Let's start out here. So we know the general formula is CnH2n. So if my carbon is 2, my hydrogen is 4. If my carbon is 3, my hydrogen is 6. Carbon of 4, my hydrogen is 8. Carbon of 5, my hydrogens are 10. Carbon of 6, my hydrogens are 12. And the most common structural isomers of each of these are listed and named here, so that's going to help me in drawing out that structural isomer. So C2H4, there's only one way to draw this, which is why there's nothing special about the name. There's no ones like we see in these bottom 3. So I have a carbon-carbon doubly bonded, and then I'm going to have 4 hydrogens, 2 on each carbon. Each carbon has 4 bonds, each hydrogen has 1 bond. They're nice and stable. That is ethene. Propene has 3 carbons in a chain. And no matter how I draw it, the double bond is going to be between the first and the second carbon. Remember, if we count out where the double bonds are, or any functional group, we count from the carbon that is closest to the functional group. So drawing this out with the double bond between these two would be the same as drawing it out between these two. So I don't need to go to the trouble of calling it prop 1-ene. No matter what, there's only one way to draw this. So I need to finish drawing out my hydrogens. And that is propene. But 1-ene, I have 4 carbons in a row, and my double bond is going to be between my first and second carbon because of this 1 here, means it has to be on the first carbon. And then I fill it out with the rest of my hydrogens. Now we could have but 2-ene where my double bond is here. So that is another possibility. If I were to draw it here, it would be the same as having drawn it here, because again we start counting from the carbon closest to my functional group, which happens to be the double bond in these instances. Next up we have pent 1-ene. So 5 in a row, 1, 2, 3, 4, 5, and the 1 is telling me that it's between my first and second carbon, so there's my double bond. Finish it up with all the hydrogens. If I were to draw this again, I could have pent 1-ene with my double bond in between these 2 carbons. If I wanted a different structural isomer of it, I could put my double bond here, and that would make it pent 2-ene. And those are my only 2 structural isomers that have the 5 carbons in a row. If I wanted to start getting fancy with it and do a methyl group or something like that, then we start getting a little more in depth than we need to here. Okay, finally, hexene, 6 carbons in a row. Again, it's telling me that my double bond is between my first and second carbon, which again I could have drawn on this side between those 2. And then my hydrogens go all around. I'm going to save us a little time and just draw the lines where they would go. You would not want to do this on a test or on your homework, but just to save time, we're going to do that here. I could put my bond between my second and my third carbon, or I could do it between my third and my fourth. So I could have hex 2-ene, or I could have hex 3-ene as normal alkenes as well. Okay, some trends. We're used to dealing with trends on the periodic table. There's certain trends when dealing with alkenes, and we talked about some with alkanes already. First of all, we know that double bonds are stronger than single bonds. That also means that they are shorter. Okay, the stronger, shorter, they're going to be held together more, which means they're going to be more reactive, which leads us to this next point. The activation energy, EA activation energy, is lower than the alkanes were. So it doesn't take a whole lot of energy because it's slightly unstable from having those close carbon-carbon bonds. And it's easier to react. So it's more reactive than the alkanes. We have some common reactions like we did with the alkanes. The first common reaction is an addition reaction. That's where the double bond becomes a single bond with space for 2 new species to react. So let's take a look at the most easy general form for us, looking at ethene, our most simple of the alkenes, just 2 carbons, 4 hydrogens, reacting with some compound. Let's say it could be O2, so X and Y could be the same thing. could be hydrochloric acid, HCl, whatever we want it to be. This is just a general form for us. Reacts, these coming in, they break apart, they break this double bond. One of these substances, one part of the substance, the X, goes on this side of the double bond. The Y then has to go on the other side of the double bond, because when we break that bond, both carbons need something else to bond to. That's why we have them in on different carbons here. Common addition reaction. First of all, and this is very common on IB exams, if you're unsure if an alkene or an alkyne, or just in general an unsaturated hydrocarbon. So you might be given a question that says, is there an unsaturated hydrocarbon present? What you would do if you saw that is say, I'm going to add it to bromine water. So bromine, Br2, dissolved in water at standard temperature and pressure, STP, so room temperature and pressure 1 atmosphere. So we don't need special conditions for it. I just take this yellow brownish bromine water, add my substance to it, and if an alkene or an alkyne, my unsaturated hydrocarbon, is present, the solution is going to go from a yellow-brown, which is what bromine looks like, to a colorless solution. So very nice, easy, macroscopic way for me to visually determine if there is an unsaturated hydrocarbon present. And the example of what would happen here, I have my double bond. Rather than XY, we see what we're actually dealing with. We're dealing with Br2. When that double bond breaks, one bromine goes on one of the carbons, the other bromine goes on the other carbon. I have 1,2-dibromoethane. 1,2-dibromoethane is my product. My second common type of reaction is polymerization. So polymers, they are long chains of monomers that are joined together. Some common ones that we see in everyday life, we have DNA, we have proteins, all sorts of wonderful natural things. And we also make things artificially, like the plastic in our bottles that we are drinking from. So polymerization can occur quite often with an addition reaction. And the most simple example is if I had a big container of ethene, C2H4, and those double bonds break. I'm going to get some C2H4 radicals. They want to bond with something, and since I've got them in a big jug together, they're going to bond with one another, and I get this part of a polymer chain. Now, quite often, we're going to draw this out. We're going to put some brackets around here, slightly longer line on either side, with a subscript of N. So this repeating unit keeps going on for some amount of time, N, and then sometimes they'll even show you how they end this. Maybe there's just hydrogens on the end that ended up with a CH3, something like that. So sometimes we'll see that that's how they end.